Hi guys, I'm not sure when you watched the previous part of the video, but for me the creation of it was last morning, almost 24 hours ago. Sorry, life intervened, but hopefully you can still make good use of this video. Alright, where we stopped, we were using the node voltage analysis on the Zener diode, and we marked this node. Why does it do that? We'll mark this node V, and we said, well, we want this V to be V Zener, and we said the condition for maintaining that is I2 has to be greater or equal to 0, right? Because from the IV characteristics of the Zener diode, you're not going to have I2 less than 0 going through the other direction at the breakdown voltage of the Zener diode. All right, so hopefully that makes sense. All right, if not, just review the previous part. We use the Kirchhoff laws or standard analysis in the node voltage analysis, our standard tools. I1 minus I3 have to be greater or equal than 0, greater than or equal to 0. Therefore, using again the same analysis we use typically in node voltages, Vin minus Vz divided by Ri minus Vz divided by RL greater or equal to 0. And I ask you to derive this, to rearrange this, to derive the equation in terms of RL, and here I have it in the box, and you may have put it in a slightly different form, but this is the equation. RL has to be, the load resistance has to be greater or equal to Ri divided by Vi divided by Vz minus 1, and that's all in parentheses. Okay, so look at this equation for a second. Okay, first of all, let's remind us what is Vi and Ri. That's some source that's delivering the voltage to the voltage regulator. And actually, this is essentially some sort of a Thevenin resistance for this load, and this is V Thevenin for this load. We don't know. It could be some other linear combination of linear elements like sources and resistances, but this is one way we use the Thevenin equivalent. We can just say we don't really care what it is. All right. Okay. And if you recall, it's no trick to control the voltage to the load resistance that is large. It is hard to do it, of course, when it's small. So this is what this is the equation that we just derived that defines the range, and we can see that it helps to have Ri that is small. So the Thevenin resistance of the source, if it is small, it helps us maintain the voltage, right? And what is the other thing? Let's look at the denominator. First of all, there is a condition, just looking at the denominator, that Vi has to be bigger than Vz, and we knew that, right? That we have no hope of maintaining Vz across the load resistance if the input voltage is smaller than Vz, all right? So, but the factor by which Vi is bigger than Vz is also important. The larger that factor, the greater than 1 it is, the smaller load resistance we can have and still maintain the voltage across it. Okay, so think about what this equation is telling you and see if you would get comfortable with it. All right, there's another way to look at the voltage regulator with the Zener diode, and let's do it this way. Okay, so we can look that if we have Vz here, okay, there's some current, let's call it I through the diode, all right, that we need to have positive. At some really small RL, and let's plot this current versus the load resistance. What's going to be the situation if RL is 0, say right here. Well, if RL is 0, that means this voltage, well, let's call this the voltage across the diode. This voltage across the diode is going to be 0, right? Because RL is in parallel with the diode, and so no current will flow. Okay. As resistance grows bigger and bigger, the diode is still off, and the circuit just consists of these two resistors, right? Because the diode, we can think of it as an open circuit until the breakdown voltage, right? And then as RL grows, so does the voltage across the RL, but ID still stays zero for a while. But there comes a point where the diode turns on. What is that point? Okay, it is such a point that at which the voltage across RL, and at this point it's just a voltage divider, so this V is VI times RL divided by RL plus RI. Okay, when this voltage reaches the Zener breakdown, okay, then the current starts flowing through the Zener. Right? And more current will flow through the Zener. What shape does that current take? All right. So we can write again I diode after it starts, the Zener turns on. Okay. We can write that I diode is again VI minus V Zener divided by RI minus the current across the load resistor, which is just V Zener divided by RL. Okay? So it is inversely proportional to RL, and when RL finally reaches infinity, this is going to be the max value. Okay, so the max value of it is just VI minus VZ divided by RI. Okay, so somehow it will approach asymptotically this value, the maximum value, VI minus VZ divided by RI. Okay? And that's going to be when RL is very, very, very large. This term will fall away. All right? So we can think of this value, this I max, through the diode as some sort of a current reserve. So when we have a very large load, we ensure that the voltage across the load doesn't increase, okay, to ultimately to the value of input voltage if we just use the voltage divider, right? If we just use the voltage divider, then if you notice this equation, just from the voltage divider rule, then the V Zener then the voltage across the resistor, at this point it wouldn't be V zener, would just, as RL increases and increases, would start approaching VI. Okay? But the voltage regulator prevents that by essentially sucking away some of the current that would have otherwise been going through the load into the Zener diode. And the maximum current that it could suck away is given right here. Okay? And as the load starts then dropping, as resistance starts decreasing from that value, at some point more and more current flows through RL, and at some point it hits to the point that where the current through RL reaches that maximum value. Okay, at this point, essentially for this RL, IL equals I max. Right? Because they're just related by subtraction, this current. So whatever doesn't go through the diode goes through the resistance. Okay, so IL equals this I max that I just showed here, and there is no more current reserve in the Zener diode, and then we can't regulate the voltage anymore. Okay, so that's just kind of an alternative viewpoint. It's not really mathematically too different, but this is how you can think of it. The Zener diode serves as some sort of a ballast that takes the excess current when the load resistance is large, and then as load resistance gets smaller and smaller, the current through the Zener diode decreases as the current through the load resistor increases, and the current through the load resistor can increase up to this maximum value that we've derived here, which is just V in minus V Zener divided by Ri. Okay, and as you notice, again, the smaller Ri is, the more of this ballast current we can have. All right, but you know, at some point, of course, our Zener diode might have some sort of a maximum current rating, and so that we don't burn it up, and maybe we cannot say 100 volts and regulate it at 6 volts V Zener and do it with a small input resistance in such a way that we get a ton of current through the Zener, because we might burn the real device. Okay, but on paper this is what it looks like. All right, so you can think about it this way, and then we'll do the IV characteristics of this as well.